Hello, my name is Abdullah, and today we're going to be going over the Beer-Lambert law, which is a part of Unit 3.13 of AP Chemistry. In today's video, we're going to be going over what the Beer-Lambert law is, how it can be applied, and how you're going to be able to use it to succeed on your AP exam this coming spring. And so we're going to be going over some example problems and going over potential resources that might interest you as well in order to maximize your understanding of the subject and ace your exams and your class. To begin, the Beer-Lambert law describes a relationship between the absorbance of light by a solution, the concentration of the absorbing species, the length of the light through the solution, and the molar absorptivity. As you can see here, there's a formula with A equals epsilon Cl, which is absorbance, the molar absorptivity, the concentration of the solution, and the path length of the light through the solution. So I'm going to let you pause here for a little bit just so you can write this down for your notes and memorize this, because this is something very useful to know at the top of your head, even if it's provided on a formula sheet. So here's the components of the law, though going into a little bit more detail on what each variable means. Absorbance measures how much light is absorbed by the sample, and it is directly proportional to the concentration of the solution and the path length of the light, which means that as the other two variables increases, so does this. Now, molar absorptivity, which is epsilon, is a constant that depends on the substance and the wavelength of light is being used. And higher values means that the more light is being absorbed, which means it has a stronger absorption. Now, concentration, C, is the amount of solute in the solution, typically measured in moles per liter, which is basically how much of the actual chemical being measured is within the total solution being experimented on. And now path length. Path length is the distance that light has to travel through the solution, which is usually measured in centimeters. It's always very important to make sure you're watching out for your units, because they are going to be asking for those, and you want to make sure that you don't lose some easy points because of units. So understanding the law. So here you can see an image depicting how the law works, but we can go over the proportionality aspect of it as well. With the Beer-Lambert law, it shows a direct relationship between the absorbance, the concentration, and the path length. If the concentration of the solute increases, the absorbance also increases, assuming that the path length and epsilon remain constant, because as there's more substance within a certain solution, that means less light is going to be able to get through because it is absorbed by the solute being introduced to the solution. And in most cases, this absorbance increases at a linear rate with the concentration, provided that the solution is diluted and follows the ideal behavior. So here are some actual applications of the Beer-Lambert law, because there will be applications of this in many different fields. So determining the concentration of something by solution, you're able to do that by using the Beer-Lambert law and absorbing it at a specific wavelength. Then environmental monitoring, which can be used to measure the amount of pollutants and certain natural elements like water, air, and soil by using light and seeing how much of it is being absorbed and comparing it to how much would be absorbed by common pollutants that could be contaminating the specific specimen. Now in pharmaceuticals, we have an image here of pills and other drugs being made, and so Beer-Lambert's law is very useful here since it helps analyze the concentration of the active ingredients in the medication. And then biochemistry, which you can use this law in order to analyze things like protein concentration and how enzymes are being cased within the specific specimens. So there are limitations to the Beer-Lambert law that are very important to note, such as high concentrations. Very, very high concentrations, deviations from the linear relationship may occur due to factors such as solution turbidity or interactions between the solute molecules. And on top of this, the path length, the law assumes that the path length is uniform and transparent, which might not always be the case due to the differences in the specific container that the specimen and the solution is being held in, or due to the way that the light is being shined, or if it's reflecting off of something. Those are things to know, but in general, they should be a uniform and straight path when considering laboratory equipment and being in an experimental environment. And now wavelength dependence. The wavelength actually depends on the different wavelengths of light. So having a precise wavelength can make sure that you have the most precise results, and making sure that it's consistent in an actual experiment environment would be important for making sure that your lab results also remain consistent. So now that you know the basic formulas that you would need to understand this unit, you're going to be able to apply them. So here's an example problem. A solution has a molar absorptivity of 25 liters per mole centimeter, a path length of 1.5 centimeters, and an absorbance of 0.65. What is the concentration of the solution? I'm going to give you a couple of seconds to write this down and take note of the different variables, and then I will show you the work that you would need to use in order to figure out the concentration of the solution. Now that you've had the time to actually work through the problem, we can go over on how you can solve the problem and what solution we got by doing the steps. So first, in order to find this, you need to rearrange the equation that we've been given in order to isolate C, so that since we've been given all other values and now we're looking for the concentration. And in order to do that, we would take the original formula and divide it by epsilon and path length in order to remove everything and just keep the concentration by itself, which would give us concentration equals A over epsilon times length. And so now that we have these formula, what we can do now is that we can use the values that we've already been given by the problem and add them in to go and find the actual concentration of this particular solution. So now you can see here that C equals 0.65 over 25 liters per mole times 1.5 centimeters, and that after evaluating it using a calculator or using some other form of evaluating, you can get the concentration of the solution is equivalent to 0.0173 moles per liter. And that should be the way that the final solution is presented. Make sure that you take note of the units, because you don't want to lose easy points on units when you did all the hard work already. Here are some additional resources now that you've gotten the basics of this unit down. 5 question problems and the document to these problems. If you can't see it, if it's been cut off a little bit, or you want to work on it on your own time, those will be provided in the description, as well as additional videos that I found really useful in understanding the concepts provided by this unit. Overall, this has been very helpful to my understanding of Beer-Lambert's law, and I would recommend that you would complete the problems and look at the solutions eventually, which will again be provided in a document linked in the bottom of the description. Thank you for watching. I hope that my video will help you on the AP exam and your class and wherever your journey may take you. Have a good evening.